Hi, this is Greg from Structural Toolkit, and this is the fifth video in our two-storey residential house design series. In our previous video, we went through almost all of our floor and lower roof framing, and now we're up to designing our brace frame. If you remember back to our second video, we calculated our bracing forces, placed our standard bracing, and concluded that we needed a brace frame at the front of the garage, which could take a lateral load of 8.3 kilonewtons. Brace frames in a residential house can come in various forms, but generally speaking, a brace frame will comprise of at least 2 columns and 1 horizontal member, with the general mechanism being that we want to transfer the horizontal wind forces down to the footing whilst keeping the deflection at the top of the frame within a specified limit. Now, unlike the rest of our framing members, the horizontal member of a brace frame is usually going to have a fixed end connection to the columns. The base of the columns will then be either pinned or fixed to the slab or footings. By fixing the base, you will have a stiffer frame and possibly smaller sizes. However, fixing the base results in the need to deal with another moment connection and also the requirement to ensure the transferred moment can be dealt with in the footing. Pinning the base will result in simpler base fixings and only an uplift component to deal with the footing. This is the approach that we will adopt. Care needs to be taken with the detailing of the base fixing, as you can inadvertently attract moments and overload the connection or pull out hold down fixings. One of the most typical brace frames is a frame that spans over an opening. In its most simplest form, it will consist of 2 column PFCs and 1 horizontal PFC lintel. The PFC lintel will have end plates that are bolted into the flanges of the PFC columns at each end, forming a fixed or rigid connection. An alternative to this is welding the lintel to the column on site, though typically this isn't the preferred method. The PFC columns are then fixed at the top into a roof or floor top plate to ensure that the frame is anchored into the timber framing and will allow for adequate transfer of bracing forces into the brace frame itself. The bottom of the PFC is then fixed to the concrete footing with a base plate and bolts. A pinned connection can be idealised here by having the bolts be on the inside of the PFC flanges. For a fixed connection, you would place them on the outside and proportion welds and base plate thicknesses accordingly. So with all this in mind, we'll then be designing our brace frame with 3 PFC members. The lintel will have fixed ends and the columns will be pinned at the bottom. We already have our horizontal load calculated, so we can get right into it. However, before we draw out our model in analysis, it will be useful to get an idea of what our vertical forces over our lintel are doing. For our opening, we are going to be supporting some roof and brick veneer wall above. The span is such that using an isolated angle lintel for the brickwork will not work, so we'll need to use a PFC and angle. We'll start by looking at a design of just the lintel, and so we'll create a new section just for our brace frame. For our lintel design, we'll be using a PFC and angle, and so we'll open the corresponding module. This design module works in a similar way to our previous beam and lintel designs. So we'll go ahead and input our span, being 5100. Our effective length will take the full length, which will be conservative. The roof joists don't span directly onto our lintel, so there won't be direct lateral restraint. However, because the frame will be directly below the roof, there would be some level of lateral restraint in reality. This is something important to think about when considering torsional rotation, which we'll touch on later. Our RM will then be 1.13. Now for a connection like this, the supported wall will be about 240 mm thick, with the PFC in the internal stud and then the angle supporting the external brickwork. In order for the brickwork to properly bear on the angle lintel, you'll usually need the leg that supports the brickwork to be sufficiently long, and so often a 150 by 90 unequal angle will be specified, with the 150 leg on the bottom. So we know in our case that our long leg vertical selection will be no. We'll have our angle flush with the bottom of the PFC, and so we can leave this as 0. For our loads, we'll have roof and brick veneer wall. For sheet roof, we'll be using 0.4 kPa, and for brick veneer walls, we'll be using 2.2 kPa for brickwork and 0.4 for internal stud, giving a total of 2.6 kPa. Although we do technically have a roof beam here, given the small load it would apply, it's going to be easier to just idealize a UDL using the spacing of the roof joists of 900. So we'll put that in our load width. We won't be having any floor, so we'll delete that. Our wall load above is then 1000, and we'll change it to 2.6 kPa. As we are doing a residential design, our roof live load will be 0.25 kPa. Now the deflection limits we'll be aiming for is span on 500 for dead load and span on 360 or 10 mil for total. Keeping in mind we'll want to use a thickness less than 10 mil to allow the builders to provide some grout in the joint, so we'll pick a 8 mil unequal angle. Next, looking at our PFC, we can see we'll be able to bring it down a bit, down to a 180 PFC. Obviously, this design does not reflect our fixed end connections, however, it does give us a good starting point for our brace frame, and has also allowed us to easily calculate our vertical forces for our model. It also shows that a PFC and angle of this size will be suitable for the brick veneer above. Now, something we also need to think about when designing a beam like this is that the weight of the brickwork can cause a torsional force on the section. This is mitigated to some extent due to the shear centre of the PFC section being behind the web, away from the section itself. However, a PFC section has a very low torsional stiffness, and so we will need to be satisfied that any torsional forces do not cause any instability. If we look at our house's elevation again, we can see that this PFC angle will sit just below the roof space, and so the roof framing itself will provide some restraint on the PFC from rotating. The amount of wall we are designing for is also relatively small, so considering all this, we can be satisfied that the torsional forces will not have a significant impact for this design. If there was a significant amount of brickwork above, or no adjacent framing to tie the beam in, then you may need to consider welding a plate between the flange ends in order to provide sufficient torsional capacity. You can use analysis standard to determine the rotation of a beam under torsional loading. We've done a video on this concept previously, a link to it will be included in the description below. With our standalone lintel design done, we can move on to our actual brace frame model. To perform our model analysis, we'll be using Structural Toolkit's analysis package. We've already gone through how to use analysis in several previous videos, so check these out if you're unsure as to how to set up your model. For our brace frame, there's a few ways we can go about it. We could use the wizard feature, which based on some initial inputs, we can have a brace frame with various forces set up for us. This option is available to users with the analysis standard package. The other way is to set it up ourselves, which is the way analysis light users will need to do it. So that everyone can follow along, we'll quickly set things up ourselves. You can skip ahead in the video as needed. We'll start by opening up a blank analysis document and call it brace frame GL02. We'll be interested in dead load, live load and wind load, so we'll pick the last option here. You can of course create your own combinations instead. Our frame height is about 2.6 meters, so we'll first draw in our first column. This is our floor to ceiling height. Now to tie the frame into our timber framing, the top of our frame columns will be fixed to the top plates at roof level, as we discussed at the start of the video. This will mean in our case our columns will extend slightly above our lintel's height, so we'll need to incorporate this into our model. Our lintel will be about 2.3 meters high, so we'll split our column at that height. We'll then copy our column across our span of 5.1 meters. And then draw our lintel in between. For users using Analysis Lite, you won't be able to draw more than 4 nodes, so the additional lengths above the column will need to be accounted for in some other way. Next, we'll then pin both of our supports. With our model drawn up, we can now choose some sections to start with. We arrived at a 180 PFC for our lintel with our simple design, so we'll start with a 180 PFC for the columns and lintel. With our section set, we can now look at our loads. What we'll effectively have is a set of UDL loads and then our horizontal ultimate wind load. We already know what our UDL dead load and live load will be based on our lintel design, where our dead load is 0.36 plus 2.6 being 2.96 kilonewtons per meter, excluding self-weight, and our live load is 0.23 kilonewtons per meter. These are both working loads and will be factored to ultimate later. Our wind load UDL will just be our roof joist centres times our ultimate wind load with factors applied, equaling 0.67 kilonewtons per meter. Finally, our horizontal load is 8.3 kilonewtons, noting this is ultimate, and is a value we calculated in an earlier episode where we went through our standard bracing. With our loads determined, we can now create each of them and then apply them to our model. Starting with our dead load, and then our live load, our wind load UDL, and finally our wind point load. Next, we're going to start applying them to the model. We'll be applying our wind point load at the top of our frame, where it fixes into the roof framing. The final thing we'll do is create an additional load combination, being for our wind deflection, which will be our wind case multiplied by the serviceability ratio of 0.68, which we calculated in our wind analysis in our standard bracing video. And now we're ready to analyze. If we had used the wizard instead, we could have skipped a few of these steps, as most of our geometry and load setup is done for us. It would be a simple matter of deleting unwanted loads and redefining others. Brace frames like these are typically critical for horizontal deflection, especially when there is no floor load involved. So we'll start by looking at our deflection. We can see our horizontal deflection has a max of 9.8 millimeters, which is height on 265. Looking at AS 1170.0, Table C1 has a few recommendations for deflections of columns or walls. Keeping in mind we have brick veneer, so we'll have a lower tolerance for deflection than if we had lightweight cladding. Under wall elements, columns have a side sway recommendation limit of height on 500, and masonry walls for in-plane loading have a limit of height on 600. For our brick veneer construction, a suitable limit might then be height on 500, so we'll adopt this for our design. This means we'll need to increase our section sizes. Given we're quite a bit off height on 500 at the moment, we'll go up 2 sizes for both the columns and beam, being a 230 PFC. Analysing again, we get a horizontal deflection of 5.2 millimeters, which is height on 500, being right on our limit, so we'll go with this. Depending on the location of the brace frame and surrounding construction, this limit could be reduced at the discretion of the engineer. Looking at our vertical deflections, we can see they're fairly minor, and even less than what we calculated in our simple lintel design due to our fixed ends. The next part of this process is to then check our design forces for both the column and lintel, and also the end plate connection for the lintel fixed to the side of the column. For those of you that have Analysis Standard on our current subscription, you'll be able to do this fairly easily by converting each member into a steel design for each combination. You can also do this for an end plate design. Alternatively, we'll have to manually create this design and transfer the values. So that everyone can follow along, we'll be creating them manually. Now, to keep things simple, we'll take the maximum moment, shear and axial force from each of the combinations combined. This is conservative, but as deflection is typically critical in brace frame designs, it's a reasonable approach. Starting with our lintel design, we can see we have a maximum moment of 14.2 kilonewton meters, a maximum shear of 10.7 kilonewtons, and a compression of 6.2 kilonewtons. We'll then open up a member design and input these values. We'll pick our 230 PFC and then input our loads. Next we'll do our segment length, which will be 5100. Our alpha M based on our moment distribution is roughly 2.35. It should be noted that we will be ignoring the angle for our capacity check to keep things simple. If we can prove that just the PFC works, then no further refinement will be necessary. For the effective length factors for bending, we can look at the LE tab. With fully restrained ends and the load being applied within the segment and through the shear center, this gives us a KE of 1.0. For the effective length factors for compression, in the Y direction we have the PFC columns at the ends which provide very little torsional or rotational resistance. Therefore, looking at figure 4.6.3.2, the KE would be 1 for a pinned end connection. In the X-axis, the ends are fixed to the columns, forming a rigid jointed frame. As our beam would be a braced member, our KE should then probably be somewhere between 0.7 to 1, And so to keep things simple, we'll just go with 1.0 for now to be conservative. Alternatively, you could look at clause 4.6.3.3 to determine what your actual KE will be, where you would also use the stiffness ratio for rectangular frames. We can see that our lintel then comfortably works under these loads. Next is our column, which if we look back on our model, has a moment of 14.2, a shear of 6.2, and an axial of 11.5. We'll then copy our current member design, input our forces. We'll take our segment length to be from the lintel height to floor level, which is 2300. Our alpha M for this will be 1.75. As our column is a sway member, we'll need to include a KEX of 2.2, based on the sway member diagram from figure 4.6.3.2 in the steel code. Once again, you could look at refining this value using clause 4.6.3.3, but for our design, we will just adopt 2.2. Using these values, our column also works quite comfortably. Our end plate design is then next. We've already gone through in detail how this design works in our end plate design video, so check it out if you're unsure about any aspect of this design. As we'll be fixing our lintel to the side of our column with an end plate, we'll be interested in the forces at the lintel member ends. For this case, it does happen to be the same forces we used for the lintel member design, but this won't always be the case, where we can see we have a moment of 14.2, a shear of 10.7, and an axial of 6.2 again. So we'll go ahead and open up an end plate design module. We'll select our section and then enter our forces. Note that in the design, tension forces are critical for what's checked in this module, so you'll need to remember to enter any tension forces if there are any. In our case, we don't have any tension forces, so we'll just leave this input as 0 to be conservative. Our member pitch will be 0. Next, we then have our connection geometry. We'll start with a 16mm end plate and 4 M16 8.8 TV bolts and see how we go. We want to keep the plate as wide as our PFC width, so we'll choose 75mm. We can see that both our bolts and plate currently fail. However, we can see that our design M star is being determined by a minimum requirement of 0.5 MBX. As default, our phi MBX input is just the phi MSX. We've already worked out what our actual phi MBX is, so if we look again at our member design, we can see this value is 61.6 kilonewton meters, so we'll use this instead. This gets our bolts to work, meaning we can keep our M16. We'll just need to bump up our plate to 20mm. And with that, our end plate design is complete. This module doesn't do any stiffener checks, however, so if you are interested in that, you'll need to look at the portal knee module. For a residential brace frame, nominal 10mm stiffeners are typically used, so we'll pick those. We'll also be full strength butt welding our lintel to our end plate. The final part of our brace frame design is the base plate, where we'll need to ensure our bolts have enough pull-out capacity. Looking at our 0.9 dead load plus wind load reaction, we can see we don't actually have any pullout force, so we'll just pick 2 M16 ChemSet 101 for each column. Now there has been a lot of manually calculating and reading numbers and inputting them into cells for this design, so somebody checking this may have a hard time working out where all the values came from. It might be appropriate then to draw and write down how the model was created and how the loads were determined on either a document or piece of comp paper. For the purpose of this video, we'll be omitting this however. One final thing you may want to do on this model is to set up print views, so that when you export your comps to PDF, you'll be able to show all the necessary information. We won't be doing it in this video however, so have a look at our print views video if you need to know more. With our brace frame design complete, we can move on to the next section of our design, being our concrete raft slab, and then the rear retaining wall and front masonry fence. We'll be going through this in our next video, which will be the final video of this design series. If you have any questions, feel free to contact our support team via email or by calling us. Thanks for watching.